Thanks all for coming, also to the online participants. I hope all of this is working well. So it's my pleasure to introduce the speaker of today, Professor Cigdem Yalcin from Istanbul University. If I remember correctly, I was in Istanbul in 2018, wasn't it? When you actually organized a symposium on disordered systems, because you lead a working group on nonlinear sciences. And last year, so it's already Cigdem's second visit here. She was here end of last year. She organized the same symposium online and like a hybrid at KIT. So this was quite a pleasure. So it's very nice that I was once invited to Istanbul to present there, and now it's the returned favor. You are here at KIT to present your research and your profile. So please.
First of all, I would like to thank to LNP 5 and International Office of KIT for this organization, and of course, I would like to thank to Professor Hagenmeyer and my host, Benjamin Schaeffer, for this excellent scientific environment, really providing this one to me. Thank you so much. And today, as you see, I'm from Istanbul University Physics Department, as Benjamin said. Today, I will talk about a new perspective on complex network representation. We performed this study with Berk Önder, who is my master student in Istanbul University. So we plan to do some final adjustments and submit very soon. So first, I will talk about complex systems. Actually, by taking advantages, this is not the complexity community. I want to make some advertisement of complex systems. And then I will talk about complex networks. Then I will show these two very well-known algorithms to convert time series to complex network. Then by developing this electrostatic graph algorithm, by developing this, I will propose convert spatial time series to complex network. We call it gravitational graph. And then I will use the data from Istanbul, air pollution data from Istanbul, to illustrate this study. Actually, now we can just ask our motivation why we need to convert time series to complex network. Actually, the answer would be that, as you will see in a few minutes, I will show you the complex systems, features of complex systems. So naturally, the feature of complex systems are very different than linear systems. So that's why you need to introduce and develop new techniques. For example, Christian Beck just gave his talk, and he proposed a super statistics is a very powerful tool to classify complex systems. Or Konstantin Tselis proposed the QE statistics, which is also called generalized statistical mechanics. Is also a very powerful techniques to understand complex systems. So complex network is also another techniques to understand complex systems. Actually, a complex network theory is also, we can call it, is a statistical physics interpretation of old graph theory. So that's why we convert spatial time series to complex network, because once you have a complex networks, that time you can have a benefit. You can have several benefits to use its offers. What are their offers? Actually, I also put here capturing nonlinear relationships and identifying influential nodes. I will give about it on the complex network part, actually. Okay, so here I will put some definition of complex systems, but I will have an anecdote to say it now. It was in 2017. I was in some for complex systems summer. So we were about 40 people from all over the world. We were generating definitions of complex systems. So finally we have a list longer and longer. Then finally that was the final definition. Complex systems are the systems complexity scientists study. So just trust complexity scientists, because if complexity scientists work on that topics, they are complex systems. Okay, so one definition comes for first feature. Complex system consists of many components interacting with each other and their environment in multiple ways. Actually, what type of interaction? These are nonlinear interactions, not non-proportional interactions. And the example here is the billions of interacting neurons in the human brain. So these interactions, a feature of complex systems, cause to the next feature, this one. So its properties of complex systems as a whole are very different and often unexpected from properties of their individual components, because that is emergence. That is the emergence feature. So as you see in this example, so the cells comes together form tissues comes together form organs, and then it goes, but it is unplanned, of course. So this is the emergence. So it's also said that the whole is more than the sum of its parts. So 2 plus 2, it's not equal 4 for complex systems. And here I have to remember and remind you Murray-Gell-Mann's contribution to complex systems. So here you see the Murray-Gell-Mann, who is a Nobel Prize winner in physics 1969, because of his outstanding contribution to high energy physics for classification of elementary particles and interactions. So he got the full Nobel Prize in 1969. Because of he got the full Nobel Prize, it was not able to get another Nobel Prize. So that is because he had a very outstanding contribution to QC and some other concepts. So after he got the Nobel Prize, some 14 years later, with his colleagues, he established the Santa Fe Institute. So Santa Fe Institute, it was the first institute to study complex systems and to disseminate complex systems as a separate concept for interdisciplinary, not only physicists, of course, even the journalists or some from every disciplines. And he also wrote this book, Quarks and Jaguar. It's about simple systems versus complex systems. So it was, of course, great chance for me to meet him and visit him every year during almost 10 years, and published also together. And unfortunately, my last visit for his funeral ceremony in 2019. So his contribution to, because of his contribution to complex system, is also known a pioneer of complexity science. So he says for emergency, you don't need something more to get something more. That is what emergence means. Okay, so if we go to the next one, complex systems may self-organize to produce non-trivial patterns spontaneously without a blueprints. So this is the self-organization. So self-organization is also a very attractive topic to examine it. Even people make some experiment by using the rice or sand pile or many things to understand these phase transitions actually. So self-organization actually, why it is interesting? Because there is no central control, central leader, any leader, and also any leader from the outside. And another feature of complex system, of course, it is expected, tend to change their states dynamically, often showing unpredictable long-term behavior. So we put this example from finance, so we can see different areas, examples here, dynamics. And complex systems may adapt and evolve. So for this feature, actually, I put it here, immune systems, because this is also a very common topics for complexity scientists. Even before COVID-19, complexity scientists was working on epidemics for different virus. And complex science can be used to understand, manage a wide variety of systems in many domains. So it gives us how it is interdisciplinarity. And methods, as I said, methods, we need to have proper methods to understand complex systems. That's why here, if we have a time series or spatial time series, we convert it to complex networks to understand its underlying dynamics of the time series. So here also I want to show this Manlio, Domenico and his friends produced this complex explained project. I was also part of his translation project. So complex networks, you see here the of course complex networks, as you see, might be natural or man-made systems. And this network-based representation actually allows for the examination of systems' structural properties, interactions, and emergent behavior. That is what is the prominent feature of complex systems. And also, I mentioned two feature related with complex network. One is this capturing non-linear behaviors, because you cannot see some non-linear dependencies and relations on the time series, but you can see them on the complex network representation. And also you can see some critical time series, critical time points and regions also in the complex network. So as you see, the applications of complex networks, biological networks, technological, social, so there are many. And if we can also do this convert process, we can do more, we can have more applications. And now I want to show you one process, one algorithm to convert time series to complex network. So it is, the reference comes from Lucas Lacasa and his colleagues from 2008. It's a very well-known one. So they say that you have a one time series, and every value corresponds to one node here. And let's say this is this axis is time and y is corresponding value. So this first one see the second one, first one see the third one, fourth and fifth one, but cannot see the sixth one. So that means there is no age between these two. Actually, and when you follow this one, actually for just I mentioned here, you have this network. Actually, I have one more picture. It's colorful. Maybe it's better to see here. So here, this is the visible. So blue is connected. This is not visible, so not connected here, because there is a higher value between those two. Okay, one of the algorithm is this one. The another one is this electrostatic graph. So Tisiotas and his colleagues published this recently in 2021. And this proposed method conceptualizes a time series as a series of electrically charged particles, as you see here. And by calculating a Coulomb force for each pair of data, calculating, you can have this adjacency matrix. So once you have this adjacency matrix, that means you have a complex network. You can represent it. And their algorithm is simply in this way. And after this, we want to use spatial-temporal data to convert to complex systems, not only one time series. We didn't want to have this type. For example, here I want to show, this is the map. You have some different locations, and these locations corresponds to nodes, and every location have their own data. So, for example, when you calculate the correlation between those nodes, you can have adjacency matrix, and by looking at this adjacency matrix, you can have the complex network representation. So net weighted graph here, as you see, weighted graphs. So you can show it is from thin to thick line or colorful bar. So, but first we thought this one, but we realized that here we don't use actually effectively coordinates. We just use correlation, but we want to use actually a real distance. That's why we developed the electrostatic graph, and we actually prefer to use that one. But before to go that, I want to show you which topic we choose to illustrate these complex networks. So it's actually we choose air pollution topics because even in the last 2 decades, the air pollution is decreasing. It's still the largest environmental health risk in Europe. So it's very recent, a recent journal, article from a European Environment Agency. And for this topic, we want to take Istanbul, because Istanbul is a very large city and very actually really complex city. I can say that as a local one. So here you see this is the Golden Horn, this is the Bosphorus. So Istanbul, according to official record a few years ago, it was 16 million. So now probably we have a few million more. So why we choose actually Istanbul? Because actually when I look at the station for PM10, particle matter for a diameter 10 micrometers, for that stations, actually first I look this district. One is this Mecidiyeköy. It is the most busy change point for public transportation. This is a hub. So, but Kandili is a very nice district. So you see, and Maslak is a finance district, and Aksaray actually is in the center of the historical part of Istanbul. Başakşehir is very busy residence area, as you see, and Sultan Gazi, actually this photo from the factory fire, but I put this just to emphasize that there are factories there, so there is a risk always. So as you see, there are different districts and different stations. That means different character. That's why we choose the stations from Istanbul, and you see these 22 stations to measure PM10 in Istanbul here. And when we apply this correlation function to convert this spatial-temporal data to complex network, we plot this one. So you see it's very connected to each other. But actually, as I said, we wanted to effectively include the location. That's why we propose this algorithm for spatial-temporal data by developing the proposed electrostatic graph. So we have the map. So now we have the real distance by using latitudes and longitudes. We calculate this one, and then by using gravitational force, we have adjacency matrix. So in this point, also what we did, so we have the data gram per cubic meter, that is the density for air pollution. So we did also unit analysis. So it's we can confidently say that it's a very proper algorithm to use this one. Then after we have the adjacency matrix, we plot weighted graphs for, again, the same stations here. As you see, it's a different colors, and only just a little bit we see the red part here is in the city center. Actually, it's Mecidiyeköy and Beşiktaş, near Mecidiyeköy and Beşiktaş. Okay, actually, here you see the weighted graph. So we didn't define a threshold. If we define a threshold, we could see some nodes are not connected to, and some nodes are connected. But instead of that, we choose to plot a weighted graph and then change the threshold and see how the feature dynamically change. So when we change the threshold, so that shows are connected or not. For example, and we looked at many of the features. I put some of them here. For example, node degree. Node degree is the one node connected with how many edges. And when you make higher the threshold, nodes degrees are, as you see, decrease. And similarly, graph density, because if we calculate graph density with like this, 2m, m is the number of edges, n is the number of nodes. Still, similarly, you see if the threshold high, your graph density is decreasing. We also look at these features. Average shortest path length. So when you take two nodes and look at the shortest path length between those, when you change the threshold, interestingly, we see this one because something's happened here, and then network change, and then you can you need a longer way to reach the given nodes actually. And number of components change. It is, as you see, this inverse. It's going up. It's increasing because components here meaning that it is not connected to network anymore, but it was. That's why when you threshold increase, you have more components, but it will be not connected anymore with the network. And this one is network diameter. This is also similar to shortest path length. When you increase the threshold, you will have this pattern. Interestingly, network diameter goes up here. Yeah, so actually, as you see here, once you have a complex network, you can have benefit from these techniques to understand the dynamics of your data. Of course, there are some others. For example, paths. You can calculate paths or centralities, between centralities, or a statistical characterization degrees. For example, a degree distribution. So you can look at power law, tails, etc. Yeah, so actually the main message we want to give here, if we have a complex network representation from spatial-temporal data, we can have opportunity to understand real-world complex systems that depends on the locations. And also when we have that type of, we can explore hidden relationship and dependencies may not apparent in the original time series, and we can identify critical time points or regions in the time series that have a significant impact on overall system behavior. So that's why we wanted to use this data by converting. We wanted to have complex network and analyze it. Okay, and thank you.